Okay. So thank you very much for joining us. This is the last session of the Crypto Cafe before the holidays. So today we have our student Abhraneel Dutta, who is trying to present his work that been accepted to LEDACrypt, so that we are very proud of that. So questions.
Okay. Okay. First of all, thank you, Dr. Sika, to give me this for giving me this opportunity to present this before I go for the final presentation over there. So, like I think they have like half an hour presentation, but I'm not sure yet because they haven't let me know yet. So I will give you the full presentation. 20 minutes. Oh.
You must.
Yeah, so like half an hour, that includes the question.
Oh, okay. Okay.
So I think you will have about 20-25 minutes max.
Okay, so I will give the full presentation here. So after the presentation, you can like suggest me which one to keep and we can exclude the other stuff. Okay, so so we will talk about polynomial inversion algorithms in constant time for post-quantum cryptography. So polynomial inversion is a very crucial operation in many crypto systems like Bike, LEDACrypt, especially during their key generation phase. So and it is very costly operation. So to protect to protect this from this operation from timing side channel attack, we need constant time algorithm. So what does constant time algorithm do? It runs for the irrespective of the size of the input size, it always runs the same amount of time. Okay. So first one, we will talk about like Bernstein and Yang inversion. So this inversion is based on extended GCD algorithm. So what happens in their setup is we have a ring f2x over x power p plus 1, where x power p plus 1 is factored into x plus 1 times an irreducible factor. And what extended GCD does is we know that for two input polynomials f and g, it outputs two more polynomials u and v along with the GCD of f and g, and GCD of f and g equals uf plus vd. So for the Bike setup, since we are trying to find the inversion of the polynomial, so let's say we want to find the inverse of h0. So since h0 is an invertible polynomial in that particular ring, so GCD of h0 and x power p plus 1 is 1. So using the Bezoos identity, we can find the inverse of h0. So traditional extended GCD algorithm is not suitable for cryptographic applications because, like, for each step, whenever we perform a division, the degree difference may differ. Okay, so that's why it's not regular in nature. So it is so to prevent this kind of operation from side channel, the timing side channel attack. So the Bernstein and Yang gave it a constant time setup. So Bernstein and Yang came up with this unique division algorithm where the division is made by this div step function. So what does this div step function do? See, according to depending on the values of delta. So where delta is the degree difference between f and g, and depending on the value of delta and g0, it it has a conditional swap and an elimination of the coefficients. So, and they have a result like, so how does this div step help in dividing two polynomials? So whenever we have a polynomial m0 polynomial divided by a degree m1 polynomial, so it takes 2m0 minus 2m1 one many div step calls to complete the division. And for to invert a polynomial, we need 2m minus 1 many div step calls. Okay, so what they do is in the polynomial, like they reverse the polynomial. That means the most significant term becomes the least significant and vice versa. So they reverse the polynomial The input of the algorithm is f, which is x power p plus 1, and the reverse polynomial h0. And the degree difference then becomes 1. So the algorithm outputs the inverse of h0. And how many div step calls it makes? It makes 2p minus 1. So that means irrespective of the input size, that means irrespective of the degree of h0, it always performs 2p minus 1 many div steps. So that's why it is constant time. Another thing, like it also can be done using transition matrices. So each transition matrices correspond to one div step call. Okay, so for n div steps calls, we can like make we can do this matrix multiplication. So this is n step matrix multiplication. If we multiply this with the initial polynomials, we get the nth output of the div step. So U and Vn is the product of Tn minus 1 to T0. For example, this is suppose U0, U1, U, Q0, Q, R0. So also this the div step algorithm can be can be given a speed up by using this jump div step, which is divide and conquer nature algorithm. So what it does is it suppose you are doing like n div steps, so it divides this n length problem into two different problems, j and n minus j. So what it does for first j steps, it jumps from delta fg to delta j fj gj by calling the same algorithm recursively, and from there another n minus j step will get me nth output of the div steps. And for the optimal choice, j is n over 2. So
when you write it's like the optimal, it means that it's not true.
Yeah, it means like according to Bernstein and Yang, j equals n by 2 is optimal choice.
But it's proved, or it's
so it's their observation.
Observation.
Yeah. Okay, so for div step algorithm, it takes like order of n times n plus many operations for n div steps and for an n degree polynomial. And they have used like FLT-based polynomial multiplication. So number of operations is bounded by n plus 1 m log n plus m and c dash n log n squared. So in our case, like we will get so in this case for inverting a polynomial, they will perform 2p plus 1 and 2p minus 1 div steps for 2p minus 1 degree. Okay, so for both the cases n will be equal to m. So in that case, the number of operations is order of n log n squared. Okay, moving on to the next one, it is IT inversion. So this is based on Fermat's little theorem. Okay, so what it does is, using the Fermat's little theorem, it is enough to perform an exponentiation to get the inverse of the polynomial. So how it can be done in constant time? So this exponent to power p minus 2 minus 1 can be decomposed so that this algorithm works as number of k squaring. It always perform a k squaring and a multiplication, and an extra k squaring and multiplication whenever it has the exponent has ones. Okay. So for ones, it performs an extra k squaring and multiplication. For 0, it only performs its ones. So, and since we are working on characteristic 2 polynomial, so the k squaring, that means a x power 2 power k, this can be done by just the permutation or shifting of coefficients. So you can see that little example, like for if we do p equals 13, so p minus 2 is 11. For ones, it performs an extra k squaring and multiplication. Okay, so The algorithm takes log p minus 2, weight p minus 2 minus 1 many polynomial multiplications and same number of case variables. So this is a constant time. Why? Because irrespective of the degree of the input polynomial, it always performs log p minus 2, weight p minus 2 minus 1 many polynomial multiplications and case queries. And this p is public. Okay. And also like also using the for 2 to the power k squaring, the permutation can work as like we can pre-compute all the values by permutation, and then we can use it during the implementation or during the main loop iteration. Okay, so next our job was to find some other algorithms if they can potentially make the the FLT-based polynomial better. Okay, so with that, like so the key feature is like we have to make sure that the new polynomial the new algorithms has to maintain the constant time structure, and it has to perform better in terms of number of field operations compared to the previous FLT-based algorithm. They're like IT inversion.
Okay.
So first one is a CE algorithm. So what does CE algorithm do? It just takes p minus, it just factors the exponent p minus 2 into a times b. They decompose by the factorization of 2 to the power p minus 1 minus 2, and then it only has to do like this: alpha to the power p minus 2 minus 1. This exponentiation, and with the squaring, it can find the inverse of alpha. So how many multiplications it needs? Sorry, how many number of multiplication it needs? Oops, sorry. So it needs like a log b. So if the factorization of p minus 2 is a times b, so number of multiplication is log b plus weight b minus 1 plus log a plus weight a minus 1. So for some particular prime, we got better results for this. So then there is another algorithm called TYT algorithm. So what it does is it again decomposes p minus 2 into number of factors plus h, a remainder. Okay. So and then the decomposition goes like this: 2 power p minus 2 minus 1. And then accordingly it performs like for alpha to the power p minus 2, p minus 3 until p minus h minus 1, it performs h many multiplications. Now it depends on how many multiplications happening over here, which is alpha to the power p minus 2 minus 2. So you can notice that p minus 2 minus 2 is just the product of the factors ri's. Okay, so which one?
No, the previous one. They are the same exponent. Maybe p minus h.
Yeah, I think it should be minus 2. Yes, okay. Fix that. Thank you. Okay, so for the remaining exponentiation, suppose I express it as mx equals log 2x plus weight x minus 1. So for each of those exponentiations, it needs MR1, MR2, MR3, MRk many multiplications. So total number of multiplication in this case is summation of log 2 ri weight ri minus 1 plus h. And later it got improvement by just, so in this case, so it got improvement in the sense that it is decomposed in a different way, where h is taken less than some value one of the factors ri's. Okay, let's say without loss of generality, the factor is r1. So the remainder h, so decomposition is made in such a way so that the remainder h is less than at least one of the factors. Let's say the factor is r1. Okay, and
it's a sum or product.
sorry, yeah. Okay. Okay, yeah, it should be a product of Ri plus H. Yes. Okay, so with H less than R1, and then 2 power 2 power p minus 1 minus 2 is factored as it was before. So for the optimal choice, the weight of H has to be less than weight of p minus 2 minus 2. So how it improves the P by P algorithm, like the previous algorithm, it reuses some intermediate results to get the factor. So how it works, like whenever they calculate alpha to the power 2 to the power 0 minus 1, alpha to the power 2 to the power u1 minus 1, where this R1 is the summation of I equals 1 through n to the power I. So whenever we calculate alpha to the power 2 to the power R1 minus 1, the alpha to the power 2 to the power H minus 1 is already computed. Okay, so it reuses one of the intermediate values so that it reduces the number of multiplications. So this time the number of multiplications is reduced from H to weight of H. Okay, the last one is like short addition chain. So what is a short addition? This is called short addition chain method. So what is a short addition chain method? So we need to first of all, what is short addition chain? The short addition chain of a positive integer r, okay, is defined in such a way such that like you make a sequence of numbers for r, so which starts from 1 ends at r, and each of the sequence each of the elements in the sequence can be made by the sum of any two previous numbers. Okay, for example, like if r equals 18, so first one is 1 and repetition is allowed. So first one is 1, next one 2. How did we get 2? 1 plus 1. 4, we got 2 plus 2. 8, 4 plus 4. Then 9, we got 8 plus 1. Okay, so and 18, we got 9 plus 9. Okay, so shortest addition chain will be that which reaches from 1 to 18 in shortest length. So the addition chain method optimizes the number of polynomial multiplication. So it works better or more efficiently when we have larger Hamming weights, and it provides significant improvement over the other variants. So how does addition chain algorithm work? Like again, we do a similar kind of decomposition for p minus 2. Again, like sum it should be product. So product of ri plus h. Okay, and so what is different here is, so we have to make this decomposition decomposition very carefully in such a way such that this h should be in the short addition chain of one of the factors r1. Okay, let's say we pick r1 and we make a short addition chain of r1. So the remainder has to be there in the short addition chain. H has to be one of the elements in the short addition chain of R1 or any other factor. Okay, so that is the thing. So this setup, why this is helpful? This setup guarantees the computation of alpha to the power 2 to the power h minus 1 while calculating alpha to the power 2 to the power r1 minus 1. So we don't have to we don't have to do extra multiplications to compute alpha to the power 2 to the power h minus 1. So decomposition, again, similar kind of decomposition. So again, we have to do exponentiation, and we will get the inverse of the polynomial alpha.
What's E?
Oh, E is just, so this is alpha inverse is alpha to the power r minus 1. E is this product of factors. Okay, this is the factorization of the whole thing. Okay, so alpha to the power 2 to the power r1 minus 1, once it is computed, then the rest of the exponentiations can be computed with summation of I equals to 2k log ri plus weight ri minus 1 many multiplications. And so CR1 is this addition chain for R1, and we also can we also define this C11 and C12 and C2 this subset set of pairs of the addition chain elements, and they compute the alpha to the power r minus 1 with the help of this these elements over here. So number of multiplications in this case is less than or equals to summation log ri weight ri minus 1 plus 1. So this happens to be the best result for the IT inversion, for the IT variance. So what we have observed here, like for different primes, P from 10K to 40K with different weights for P minus 2. So with we applied their decomposition method, like optimal decomposition method, and we can see, like for example, we can see for 10499 the number of multiplication for IP, number of polynomial multiplication here we are comparing. So number of polynomial multiplication is 16. For CEA, it is higher 20, but if we consider the other two, it's 16. But if we keep increasing the weight of P minus 2, we can see like significantly better result. Like for suppose 24781, we can see number of multiplication 20, 22 for CEA, 18, and 19. And for other cases, we have like better result when we use the variance of IT inversion. Okay, so how did we do the Emra did the software implementation of all these algorithms. So what we did, like the polynomials alpha x is stored in as like divided into 64 blocks for each one of them, and defined the mul 64 for multiplication of 64 blocks, squared 64 is squaring of 64 blocks, and implemented in both x86 64 and ARM64, and used the carryless multiplication instructions for 64 bits. So the resulting block is 128 bit when they are getting multiplied or squared. So the previous functions like mul64 and square64, they are used to perform polynomial multiplication and modular multiplication. So regular polynomial multiplication calls mul 164. Mainly, this is mainly used in BY inversion because in BY inversion there is no modular multiplication. So modular multiplication happens there in the in FLT-based inversions. So FLT-based inversion algorithm calls this GF2x mod mul function. And similarly, GF2x mod squaring. So there is no squaring in BY algorithm. So that's why the GF2x mod squaring, this is only needed for the FLT-based inversion. So and if GF2x mod squared in place, this is like repeated squaring of polynomial c plus k times with the reduction of x to the power p plus 1 after each squaring. So it saves like initial and storing cost, and mostly used in FLT-based algorithms for this because squaring only happens in FLT-based variants. Okay, so this was the benchmarking. So we can see that for BYI, the number of clock cycles are significantly lower from the software implementation. So for both x86 and ARM64, and so number of and there is no number of modular multiplication and modular squaring for BYI, and how many times like mul 64 is happened 1 point. So this is in millions, 1.10 and 0.44. So this is number of block operations can be observed from the last two rows for each of the primes, and each prime is suppose for the prime 10499 there are 165 64 bit blocks. So number of operations or number of operations is like significantly less in BYI. So from the software implementation, we can see that BYI performs way better than the other two. But when we do the hardware implementation, we can skip these squarings for the case the square 64 or even the FLT-based algorithms. So in that case, FLT-based algorithms will perform better compared to BYI. So IT variance performs similar. So IT variance performs. We have seen all in our previous table that IT variance perform fewer multiplications like compared to the original IT algorithm based on FLT. So, and as the Hamming weight P-2 increases, the performance gets better. Okay, but for SSE and among the IT variance algorithm, SSE and CEA inversions show better performance compared to ITI or TYT methods. However, we already have seen that BY has better performance when we did the software implementation, like Emra did this, and but for the hardware implementation that we are going to do in future, in that case we will see better performance from the IT variance than the BY inversion. So yeah, so that's it. Was I too fast?
Any question from the audience? Emra, do you want to?
Yeah, Emra can do some inputs maybe.
Thank you, Abhraneel.
Okay,
It was a good presentation.
thank you. Should I like make something like, or yeah, let's take the question if anyone has.
Yeah.
So if we don't have any more questions, I'll stop the recording. Okay. Well, thank you again.
Thank you.
See you next year.
Okay.